Hello, everyone. Thank you very much for joining us today. We are going to get started with our live session. My name is Matthew. I am one of the teaching staff for the class, for our online class through Coursera and Udemy. And then Alexander is helping out with some technical background stuff. So Professor Impey, why don't you go ahead and welcome everybody, and then we'll get started.
Okay, welcome everyone to a live session for the astronomy online classes, and we'll get started right away.
Excellent. The first question is from Ayush, who is on with us live, who would like to know if you could discuss the significance of globular clusters in a galaxy. What does it indicate? And there was recently a massive globular cluster discovered around the Andromeda galaxy.
Mm-hmm. So globular clusters are an important part of the history of astronomy, actually, because they're the densest, richest clusters in the Milky Way galaxy, and so they're very prominent, not to the naked eye, but with a small or large telescope. And so they've been studied for over 100 years. And in fact, it was the distribution of globular clusters observed by Harlow Shapley and others early in the last century that indicated that we were not at the center of the Milky Way galaxy, because the globular clusters essentially form a nearly spherical distribution in the halo of our galaxy, with a center that is the center of our galaxy, and we were offset in that distribution. So that was the first evidence of our location away from the center of the Milky Way galaxies. So globular clusters have been important in another way because they contain the oldest stars with the fewest amount of heavy elements of all star systems and even individual stars. And so they've been used as chronometers. People have used stellar models to date the ages of stars in globular clusters to give an upper bound on the age of our galaxy, which is about 11 billion years. And so our galaxy is younger than the universe, but not by more than a couple of billion years. And also to show how pristine the universe was in terms of very few heavy elements shortly after the Big Bang, because most of those heavy elements have been made in stars. And the detailed observations of those stars in globular clusters are used to test stellar evolution models. So this particularly massive cluster that was found recently is not really an anomaly. Globular clusters are not all the same. They range from a few 100,000 stars, maybe even as little as 100,000 stars, up to several million or even 10 or 15 million stars. They vary in size in terms of their core radius, where most of the stars live, from a small fraction of a parsec. So, highly dense regions of stars very close together, thousands of times closer than the sun is to its neighbors, to core radii of several parsecs, or maybe 5 or 10 light years. So they have variable properties. The other interesting thing about globular clusters is that people in several cases have found black holes that form at the center of globular clusters, and these are in this very rare category of intermediate mass black holes, more massive than a single massive star dying, and less massive than the black holes that form at the center of galaxies. And so these are very special type of black holes to find, and we still only know of a handful of them.
Excellent, thank you very much. The next question is from Rohan, Rowan, who's on with us live. Can you explain more about gravitational time dilation? And specifically, does time really get slow near the pyramids?
Gravitational time dilation is a core prediction of general relativity. Right from the beginning of the theory, it was a prediction. But in normal environments like terrestrial environment or the solar system, this effect is so weak that it was thought that it would be very hard to measure it. And the principle in general relativity is basically that the stronger a gravitational field or gravitational situation, the slower that time runs compared to a situation with weak gravity. And so the prediction would be that clocks run slightly slower in stronger gravitational fields than in weaker gravitational fields. And amazingly, this was verified in the 1950s and then 60s because of atomic clocks. So once we had super accurate timekeeping pieces, accurate to much better than 1 part in a trillion, it was possible to take an atomic clock and two identical atomic clocks, fly one in a high altitude, sort of typically a spy plane, and then keep the other on the Earth's surface, bring them together after some hours or days, and indeed it was the case that this clock on the Earth's surface kept very slightly slower time than the clock that was flown at high altitude, because the gravity above the Earth's surface is very, very slightly less than the gravity at the Earth's surface. Now, since then, this effect has been proven in other terrestrial situations, so there's no doubt that time dilation exists. As for the pyramids, I'm not aware of anything there, and in fact, since it's to do with local gravity, the local gravity of that situation in Egypt or the pyramids themselves is just not sufficient to cause any effect in general relativity, so I'm highly skeptical that that's a real physical effect.
Excellent. Thank you very much. The next question is from an email. Ritik would like to know, is the universe infinite? And if not, what would the boundary of the universe be like?
I mean, this is a classic issue in cosmology. It's a dichotomy. Either the universe is infinite, and how do we understand an infinite region of space? What does that mean? Or the universe is finite, and if it's finite, what's the boundary? And then, of course, you want to know what's beyond the boundary, so what does the limit even mean? So either way, it seems an unusual situation. And astronomers have not formally been able to resolve this question. However, what we can say is that in modern cosmology, the universe only has an edge in time, not in space. In other words, when we look out in space through our telescopes, we're looking back in time. And eventually we look far enough out that we're looking back towards the Big Bang itself, to a time when there were no galaxies, when the universe was much smaller. And so looking out in space does not in and of itself take us to the edge of space or ask or answer that question. It just vaults us back in time towards the Big Bang. In terms of the expanding universe, there are definitely in the expansion model regions of space that we cannot see. So it's a completely core part of the Big Bang model that space in the universe is bigger than regions we can see with our telescopes because it was expanding faster than light for some part of its history. That being larger than the space we can see, the true space there is, by what factor we don't know. Could it be an infinite factor? Could space beyond the region we can see be infinite? Yes, it could. So this is allowed by the theory, and at the moment it's not a resolvable question by direct observation.
Next question is from one of our live participants, Soren Dukar. Professor, what is the most dense lump of matter that humans can touch today, and how does it compare to the density at Earth's center, at the center of the sun, or a neutron star, or relative to water?
So physicists are interested in creating dense states of matter because it lets them learn, for example, by analogy, about the centers of stars like neutron stars or white dwarfs, which are essentially entire stars that are at the density of nuclear material. So in accelerators, and especially in facilities which can concentrate laser power into a small region and therefore compress a region, it's possible to generate densities that are very close to the density of a white dwarf. So this is far denser than normal matter, because of course normal matter consists of atomic nuclei with their surrounding electron clouds, and the electron clouds repel each other and keep space empty for the large part. So normal matter is 99.149% empty space. With technology, you can compress matter enormously, and I think the factor is by more than 1 billion relative to normal matter, the densest material we might have, iron or lead or some metal like that. So that's an incredible level of compression, but it can only be achieved for an extremely short period of time, typically using lasers. Of course, the other situation where that compression occurs is in a nuclear bomb, a nuclear device, where the implosion is created by explosive force, and that creates a density of matter sufficient to cause fission or fusion to occur.
There is another question kind of in along a similar vein from Despira, who would like to know what kind of densities are created that or are necessary to start the star formation process.
So densities for star formation are not actually that high. because the regions in which stars form are very diffuse. The typical density of the interstellar medium is really low. It's of order 1 atom per cubic meter. That's incredibly low density. That's a 10 or 100 billion times less dense than the air you're breathing. So interstellar matter is very low density, 1 atom per cubic meter, that's all, typically a hydrogen atom, so a proton. And what's happening in regions that stars form is not that much different. So in a diffuse interstellar cloud, the density may be 10 or 100 atoms per cubic meter, so 100 times more dense than the typical space between stars. But that's still an incredibly diffuse region. On Earth, that would be a fantastically good vacuum. So even in the places where stars form, the density is close to a perfect vacuum. But that extra increase in density is sufficient to create gravity, which in a large cloud can trigger gravitational collapse. So the star, the gas cloud, feels more gravitational pull towards the center than towards the edges, and so it gradually starts to shrink. And as it shrinks, it accelerates its collapse because as it gets denser, the gravity is stronger, so the inward force is stronger, and it's a runaway process. So even though the starting point of a star-forming cloud is an incredibly good vacuum, just very slightly denser than the typical space between stars, once gravitational contraction starts, it accelerates, and of course in the end you can get a star formed out of that at the middle of this collapse.
The next question is from Wendy Traver, who sent an email. And Wendy would like to know what sort of biology could arise on or in the sort of world with ethane, methane lakes. And are there how many different bodies are there that have these kinds of ethane, methane lakes in the outer solar system?
So these are referring to Titan. So Titan is a large moon of Saturn. It's been explored by the Cassini probe for a number of years, and then there was the Huygens lander that was there for a very brief time in 2005, I think, and took data from the surface. And we've imaged through the clouds, dense nitrogen atmosphere with radar, and so have seen clearly that there are lakes across the surface of Titan, shallow lakes. And the physical conditions of temperature and pressure are such that it could not be liquid water. And from spectroscopy, we know that it's ethane, methane, and a little ammonia, and a little water mixed together. So these are these bizarre ethane, methane lakes on Titan. And a question of whether they're unique is a good question. In the solar system, we think they are, because we know enough about the other moons of the giant planets to say that no other moon has that composition or liquid on its surface. Whether they're unique beyond the solar system is a bigger question, very hard to answer, because essentially we haven't been able to detect moons around any of the exoplanets, the many exoplanets we've found, and then we're even further from being able to characterize those moons and say what their surfaces contain. So at the moment, ethane, methane lakes are unique to Titan. They're subject of enormous interest. The Dragonfly mission planned by NASA will send essentially drone technology to inspect the lakes, sample their material to chemical analysis, and move around the surface sampling a number of places and sort of indirectly see if they might harbor life. The question of life, though, in this medium is very uncertain. Biologists don't tend to think it's possible to have biochemistry in a liquid with that composition. They've done some simulations of that and lab experiments, but it's not absolutely ruled out. And down below the lakes, at the bottom of the lakes, where there's some more energy coming from subsurface vents and weak volcanic activity, there's enough energy to support life if the chemistry allowed it.
The next question is from Miss Sweetie, who is on with us live, and they would like to know, how are particle pairs still entangled when one member of the pair is sucked or pulled into or falls into the black hole?
Well, that's an interesting question, and really we don't know the answer, because this is getting to an area of theory of black holes where we don't have a full understanding of what's going on. Generally, the Hawking radiation results from particle-antiparticle pairs, virtual pairs, because they don't tend to be realized as real particles. They disappear back into the vacuum very quickly. Hawking radiation occurs when the virtual pair is indeed separated and one member of the pair is inside the event horizon, the other exits the black hole. So that is the mechanism for Hawking radiation. Whether that mechanism operates or what it means when you're considering quantum entanglement is unclear. But first of all, we don't even know if you could have quantum entanglement acting on particles that are in the vicinity of a black hole. Quantum entanglement is a situation, a condition of matter that has to be created in a very carefully constructed lab environment. It's not clear that entanglement occurs naturally out in the universe, and even less clear that it would occur near a black hole. In principle, however, if entanglement did occur across the event horizon, that would be a violation of one of the principles of black holes, that information is not transmitted in and out of a black hole. Because if an entangled pair spans the event horizon, then clearly the information of both particles is contained by each particle. And that, again, that violates a theorem of black holes. So the theorists suspect that quantum entanglement across an event horizon is not possible in nature. But the simple answer is we don't know.
Excellent. Thank you very much. The next question is from one of our live participants, the Divine Wanderer. How and why are we using string theory to define or create a paradigm for black holes? Is it because current thermodynamics fails or is inconsistent in the case for black holes?
It is true that current thermodynamics is insufficient to fully explain black holes. Remember, thermodynamics is classical physics. It's physics. The laws of thermodynamics were put in place in the 19th century by Lord Kelvin. And so it's physics that precedes quantum theory. It's still physics that applies, classical physics that applies in many situations. And Hawking used what essentially was classical physics to develop the ideas of black holes and the fact that they have a temperature, the fact that you can define their entropy, and so on, and how that entropy relates to their area and their mass. So the application of thermodynamics to black holes is essentially a crutch. It's an incomplete way to describe the physics of black holes. It clearly needs a superior theory to do so and to explain things like the information paradox. So theorists have reached for cutting-edge theories like string theory to try and understand black holes, since in the end we need a theory to fully understand black holes that integrates quantum mechanics and general relativity. String theory is one such theory, but string theory is not advanced enough and predictive enough to even explain the properties of black holes as we know them, let alone to make unique predictions that we might be able to test. So I would say that string theory is being investigated as a way of understanding the unusual properties of black holes and properties that cannot properly be explained by classical physics, but it's not necessarily succeeded in explaining those characteristics of black holes.
The next question is from Varun, who's on with us live. In previous talks, you mentioned telescopes that some astrophysicists are trying to build, the world's largest neutrino telescope in the Pacific Ocean to capture extreme events beyond our galaxy. Can you talk a little bit more about that, if that's true?
Mm-hmm. Neutrino astronomy is a niche of astronomy. It's far smaller than optical or radio or even X-ray astronomy, but it's an important niche because it's detecting something that's not electromagnetic radiation. Neutrinos are tiny subatomic particles that have a mass that we don't fully understand, but it's small, that travel essentially at the speed of light, that interact very weakly with matter. So neutrino detectors have to be vast in size and scale and the material they're probing to detect such elusive particles. The Pacific and the deep ocean off Hawaii has been a place for an early prototype neutrino detector called DOMAND, that's the acronym, and it was not successful in detecting astronomical events. It was too small to do so. And they have indeed tried to scale up the geometry of DOMAND and make a bigger facility, and I think they have the funding to do that. However, the limitations of putting a neutrino detector in the ocean were also revealed, because even in a deep ocean trench or in a relatively quiet region without major ocean currents. There's turbulent motion, there are fish moving around, deep sea creatures too, and it's hard not to get interference or noise or contamination with the signals that these delicate detectors are trying to measure. And so the superior method for neutrino astronomy has now been to go to a pristine ice pack, such as Antarctic ice pack, and melt boreholes, spaced a grid of boreholes down through the ice, and drop hydrophones or neutrino detectors, actually detecting the light released when a neutrino interacts with normal matter. And then when you've melted down through the boreholes, dropped a string of hydrophones in a grid of boreholes, you've essentially created a three-dimensional grid of detectors. The boreholes freeze, the detectors become locked in place, their signals pass back through the wires to the surface and are collected. So you can create an enormous volume neutrino detector. And the South Pole is home to such a detector, and now the plans are for a 10 times bigger volume detector. And this is probably the way neutrino astronomy is going to be done for the next few decades in the Antarctic, using neutrino detectors sunk into the pristine ice pack.
The next question is from Stephen Ward, who's on with us live. Would the Earth ever appear to do a transit of the Sun as seen from Mars in the same way that we occasionally can see transits of Venus? And if so, how often?
That's an excellent question, and I actually don't know the answer because I've never actually researched that. But yes, in principle and in practice, I think the Earth does transit the Sun as seen from Mars. Now, the reason it's not trivial to answer the question of how often it happens is that the Earth and Mars have slightly different tilts of their axis of their orbital plane as they orbit the Sun. So it would, of course, depend on the intersection of those planes whether you had a transit. And as we know, for example, taking our perspective on transits of Venus across the Sun's face, we know that those only occur in pairs separated by 8 years every 109 years, so 2 per century basically. So in this, if it's similar to that kind of a geometry, then we might imagine that Earth transits as seen from Mars will be correspondingly rare, but I actually don't know the number.
All right, the next question is from one of our live viewers. Angela would like to know, when do you think that we will be able to have a manned mission to Mars?
I think it's a matter of probably 8 to 10 years. That seems like a long time, and that's because it's an enormous undertaking. It's expensive. NASA's using a staged approach where they're going to do some sample return by robotic means, and then they're going to start to send infrastructure to Mars to land it on the surface, essentially lay down supplies and building materials with which to build a Mars base. Indeed, astronauts might go there before there's the material to build a base, but even then, it's a very long journey. This is a multi-year mission. And to do that just to spend a couple of days on the Mars surface, as we did with the Moon, would seem like an enormous amount of work for not much return. Remember, the Moon is only a week away, and Mars is 8 months away at the minimum. So, for that reason, it's really not worth the enormous expense, danger, and effort to send an astronaut to Mars for a very short time. It makes more sense to wait a little longer, do a little forward planning, put down materials, or maybe even drop a full habitable, inflatable habitat, and then have the astronauts be in residence for a significant period of time. Why that would mean weeks and probably a couple of months. And to do all that is going to take probably a decade. Whether it happens by NASA or by a private venture like SpaceX, of course, Elon Musk has talked about doing similar things and going to Mars. It's possible that on the timescale of a decade, SpaceX might beat NASA to the punch. It's also possible on a timescale of a decade that China might beat both of them to the punch, because China is developing its space program very rapidly, and they have plans in place, early planning for a moon base and a Mars base. And given their momentum and the amount they spend on the space program, it's growing at the rate of their budget, which until recently was very fast. they might get there first.
The next question is from Robert Brady, who's on with us live. Is there a background gravity in the universe that is based on all of its matter?
Yes, the entire universe has gravity, of course, corresponding to all the mass, and since energy has an equivalent mass, you can also put in the energy of the universe, the photons, too. And the idea that the entire universe has mass and that it influences the objects within it is actually a principle that was proposed by Ernst Mach early in the last century. Mach's is called Mach's principle, the fact that objects in the universe in the end, because gravity is an infinite range force, are actually responding to the cumulative gravity of everything in the universe. It's an interesting concept, actually. So it's just a concept. It's not clear what practical relevance it has for cosmology. But Einstein was very intrigued with Mach's principle. He thought it was correct. He thought the logic of it was correct. And so we do have to imagine that objects in the universe are aware of or are responding to the accumulation of the gravity of everything in the universe. And that's interesting because it may mean things that are slightly beyond the horizon, things that we can't actually see with our telescopes right now.
Evan Villar would like to know if you can talk about anything about the opening in the Orion Nebula in Orion's belt. I'm not sure exactly what opening they're referring to, but perhaps you can talk about the structure of the Orion Nebula and Orion's belt. What's it made of? Why does it look the way it looks?
Mm-hmm. So, as we know, constellations are just incidental groupings of stars that are typically not anywhere near each other in space, and that's true for the constellation of Orion. So the three stars in Orion's belt are not at the same distance as each other, and they're not actually at the same distance as the Orion Nebula, which is nearby in the sky. Constellations are just, as I say, incidental groupings of stars that appear to be in similar locations on the sky, but in 3 dimensions are often quite disparate. And so the stars in the belt are not associated with the Orion Nebula itself. The Orion Nebula itself is at a distance of about 1,600 light years, and it is the largest and most complex star-forming system, and the nearest, really, of its size and mass to the Earth. And so in the Orion Nebula, we see active star formation. At the center of the nebula, discovered 40 or so years ago with early infrared astronomy, is a protostar called the Backlund-Neugebauer object. So there's a deeply embedded star cluster, only visible with infrared radiation because optical light doesn't penetrate the dust. And it's been studied for a few decades as almost an archetypal region where stars are actually forming as we speak. And most of the stars in that Orion Nebula that we can put ages to are quite young, a few million, 10 million years perhaps. That's very young for stars. So it's a perfect stellar nursery with which to study the process of star formation.
Excellent. Thank you very much. The next question is from Nick Fuller, who sent an email. Do you know what is to be the next target for the Event Horizon Telescope? And would it be capable of observing an object in the southern sky?
Yeah, interesting question. I think the next target, which they've already observed and analyzed, and I expect the data will be published within a couple of months, is the center of our galaxy. They actually went to a very big black hole that's quite far away for their first published result and the first image of a black hole, M87. M87 is 65 million light years away, but it's also a 6 billion solar mass black hole. Now the galactic center is 28,000 light years away, so it's thousands of times closer, but it's also thousands of times smaller black hole. That puts it in the same ballpark as far as making an image. Turned out it was slightly harder, and that was why they didn't do it first. But they do have the sensitivity to image the center of our galaxy's black hole. And of course, that black hole's study, the study that showed there's a black hole there, won the Nobel Prize this year. So I think as a follow-up to that Nobel Prize, showing the image of our galactic center black hole will be a spectacular result. So we can anticipate that next. So after that, as a second target, people have worked out how easy to image the nearest black holes to the Milky Way are. And the next nearest examples are actually a fair bit harder. So after M87 in the center of our galaxy, we're also now talking about massive black holes in relatively nearby galaxies. But there are no black holes as big as the M87 black hole. That's one of the biggest in the universe, in fact. And also, the ones that are nearest to our galaxy are not quite big enough. So Andromeda has a black hole, we think, similar size to the one in our galaxy, but of course it's a lot further away than our galactic center. So I think the next set of targets that they might image are 4 to 6 times harder to make an image of than the first two, assuming galactic center is number 2. They have within reach a capability by expanding their telescope network and improving their sensitivity and their detectors. I think they can get that factor. And at that point, probably half a dozen new black holes are available to them. And some of them, yes, will be in the southern hemisphere. So they can do this work just as easily on southern hemisphere targets, since a number of their telescopes, not most of them, but a third of their telescopes are in the southern hemisphere.
The next question is from Raytheon, who's on with us live. The question is simple. Can you explain quasars, even though the answer may not be simple?
Sure. Quasars are, that's an acronym, or a contraction if you like, that's for quasi-stellar radio source. So quasars, in a nutshell, are active supermassive black holes at the center of galaxies in the distant universe. To appear quasi-stellar, they have to be far enough away that the galaxy the black hole sits in is not easily visible. And so most quasars are at least a few billion light years away, extending out to 12 or 13 billion light years away. Some of the most distant objects we know of in the universe have formed as some of the most massive objects in the early universe as it evolved. The black hole is active, and that's why they shine brightly in visible light, but also across the electromagnetic spectrum. So these are objects which are typically in fairly massive galaxies. They're harboring fairly massive black holes, which is to say in the range of about 100 million solar masses to about 10 billion solar masses. And they're objects that are converting by accretion in-falling matter energy, kinetic energy and heat energy, into radiant energy with an efficiency that may be 40% of E equals mc squared. And that lets them be incredibly luminous. And it only takes for a billion solar mass black hole ingesting matter, it only takes a fueling rate, if you like, of a few times the mass of the sun per year to generate a luminosity or brightness that far outshines the entire galaxy that it sits in. So that's how spectacular these objects are. When I try to make an analogy for a quasar, I visualize being in a helicopter or a plane, a slow-flying plane, high over a city like Los Angeles. And in that analogy, the population is roughly 10 million. There are about 100 lights for every person: car light, city light, street light, house light. And so you're at about 1 billion. Well, a galaxy will have 100 billion stars. So in that analogy, each light in Los Angeles is standing in for 100 stars. And what is a quasar? A quasar would be the luminous supermassive black hole in the center of the city, downtown LA, that was about an inch or a few centimeters across, and that was outshining the entire city, all those city lights, by a factor of 10 or 100. Spectacular luminosity and brightness. And that's why, as when seen from afar, the individual city lights would be invisible. They'd have faded to be too faint to see, but that super intense light from the accreting black hole is visible as a cosmic beacon across billions of light years.
My apologies, my mouse froze for a moment there. The next question is from Cheeky Bear, who's on with us live. Is it possible that ring systems around other planets could be different colors? Are there planets out there like Saturn, but with blue, purple, or red ring colors?
That's an interesting question. So ring colors would essentially depend on the composition of the rings. And sure, it's possible. We know on Earth, for example, we know of various minerals that have different colors. Often it's because there's crystalline forms within them that reflect light differently as a function of wavelength. It's pretty unusual to find naturally red, blue, green, purple crystals, but they can be found. They do exist. And so, yes, if rings were made of these exotic crystals that are colored as seen in natural light on the Earth, then those rings would look colored too. Unfortunately, those are exotic minerals. They do exist. We could find them, but they're rare. And in a typical ring system, we're talking about rather mundane materials. So most rocky material, either in the core of a planet or in the ring system, which is sort of leftover material from planet formation, most of the materials are carbonate or silicate compounds. In other words, they're just minerals that are molecules that combine silicon, carbon, oxygen, and hydrogen. And these minerals are common in terrestrial geology, and they tend to be dull brown, gray, or white in color. And so those are the colors of ring systems in our solar system, and because geology and chemistry are universal, they're very likely the color of ring systems elsewhere too. Slightly dull answer, but that's probably the way nature is.
The next question is from an email. Ruben would like to know, how likely is it that we might be able to build telescopes on the moon? And is it a good idea to have observatories there?
Yes, it's completely possible, and it's a very good idea. So let me deal with both aspects of that. The second one first. Why is it a good idea? Why would we want to? Because it's obviously hard and expensive to put telescopes on the moon compared to on the Earth or even in Earth orbit. The reason we want to is the moon, especially the dark side of the moon, is an almost perfect observing environment. It's completely dark because you're sheltered from Earth light and there's no activity on the moon. It's completely clear and sharp because the moon has no atmosphere, so there's no blurring of the light that comes in. It's completely stable because the moon is geologically dead, and so nothing is moving around or shaking around. There are no tremors. So this means it's essentially a perfect astronomy observing situation. It's true for radio astronomy too, because radio astronomy is conflicted on Earth by cellular transmissions and microwaves and TV stations and radio stations. Very hard to get radio quiet zones. In fact, the only one is near Charlottesville, where the National Radio Observatory has its headquarters in Virginia. The moon, of course, would be totally radio quiet. So it is essentially a perfect environment for both radio and optical astronomy. And you could build large facilities there. So the question of how comes up, and I think 20 years ago it might have seemed impossible, but now robotic technologies are such that most of the work could be done by robots. So you could send unmanned missions to put down most of the infrastructure and indeed have robots on the surface that would assemble the telescopes, the radio arrays or the optical telescopes from prefabricated parts. Or you could have 3D printing that actually took place on the lunar surface and even used lunar material to make some of the construction. So these technologies are futuristic, definitely, but they're not, they all exist on the Earth. They've all been tested on the Earth. And doing it on the moon would just be a matter of scale and some expense. It's not easy and cheap to make multiple or a fleet of moon missions to build one of these things. And probably in the initial stages it would need some human intervention. So there'd probably be a skeleton crew of astronauts that were routinely going to essentially a moon base and being resupplied to oversee the construction, even if that construction was mostly done by robots. So what does that all mean about the prospect of this? Well, proposals have been around for a while, and astronomers obviously super enthusiastic about it, but there are also big price tags, and astronomers can't really afford this, nor can the government in terms of how much it puts into astronomy, and that's true worldwide too. So most people think that telescopes on the moon are 20 or 30 years away, but I think eventually they will happen.
The next question is from an email, and Ravi would like to know, did dark matter originate at the same time after the Big Bang as, say, hydrogen and helium, or was it before or after that?
And that's a good question, and that gets to the point of what dark matter is. The origin of matter in the universe, in the Big Bang, occurs extremely early on, because in the very early universe, in the first fraction of a second, radiation dominated. And so particles and antiparticles were coming in and out of existence all the time, and then going back into radiation. And matter only froze out during that first fraction of a second. And the type of matter that freezes out depends on the mass. So the more massive particles are being created and destroyed at higher temperatures. So the first things to freeze out will be the quarks and the antiquarks, where they annihilate and leave a small residue of quarks to form protons and neutrons. Somewhat later than that, electrons and positrons would freeze out, and so you'd have all the ingredients of normal atoms. Now, when in that chronology, all of which occurs in the first fraction of a second, when dark matter comes into play depends entirely on the nature of the dark matter particle. The dark matter particle is not known. We're trying to detect several varieties of dark matter particle, but most of the candidates for that particle are actually quite massive. They're more massive in mass or equivalent energy terms than protons and neutrons or quarks. And that implies that the dark matter particles came into being or froze out from the radiation field before normal matter. So that's a good bet, even though we don't actually know fully the answer to that question.
All right, the next question is from one of our live viewers, Pat. Would like to know, are Wolf-Rayet stars being monitored as potential supernova candidates?
Yes, Wolf-Rayet stars. Obviously, the name is a hyphenated acronym or hyphenated name based on the two astronomers that discovered this particular type of variable stars. These are massive stars undergoing, sort of chronic instability because of changes in their fueling rate and instability that kicks in near the end of a star's life. And they do seem to be massive stars that would die as supernovae. So, in principle, there are some Wolf-Rayet stars out there where we're monitoring their irregular brightness variations, which will, at one point, run out of their nuclear fuel, suffer a core collapse, and die as supernova, leaving behind a black hole or a neutron star. The trouble is, it's very hard to identify one that may have this outcome in any reasonable amount of time. We can see Wolf-Rayet stars and decide they're in the later phases of their evolution as massive stars, but we can't pin down the time till they exhaust their nuclear fuel more accurately than probably a few 100,000 or maybe tens of thousands of years. That's pretty good in astronomy terms as a fraction of the age of the universe, but it's not very good if you're going to stare at a star and wait for it to go off. So unfortunately, our precision of predicting the true endpoint of a star that is nonetheless late in its life is too imprecise for us to actually point to a star and say that one's going to go, that one's going to blow, and we know pretty much when.
Excellent, thank you very much. The next question is from Priyansh, who would like to know, is it possible that geologically dead planets could, quote, come back to life, or would some external factor be required to cause it to come back?
I think the answer is pretty much that you need an external factor. So a planet that loses its internal heat and geological activity, it's generally a one-way passage. For example, when a planet is sufficiently massive to have a magma interior and therefore generate geological activity, it is still continuing to lose heat out into space. And that's just a law of thermodynamics, essentially. And so the Earth will be geologically active for some period of time, but not actually forever. Mars, we know, was geologically active in the past. It has enormous geological features, the largest volcano in the solar system, Olympus Mons. But Mars lost its atmosphere, and it was of insufficient mass to long-term keep its geological activity. So it tends to go in one direction only. The only way that would be countermanded was if somehow, for example, maybe due to an impact or collision, a planet gained mass. There was a collision that partially liquefied the planet and added mass to it and sort of tipped it over the edge into geological activity. That's one way it could happen. Another way that can happen, which is actually pretty unlikely, is that we know another heat source that can be added to a planet to make it geologically active is tidal heating. So if a planet somehow came to be associated with another planet in a way that their orbits interacted to cause tidal heating, then that extra bump of heating from tidal forces might push it over into geological activity. But I'm going to say that's a very unlikely occurrence.
The next question is from an email. Is the law of gravity that we have on Earth applicable in the same way on Mars? And then I will add, can you talk about how generalizable it is throughout the universe?
Well, the nature of the theory of gravity, Newton called it a universal law of gravity, was that he was enunciating a physical principle that applied across space and time, that applied to all mass and all objects in the universe. And so far, we found that to be the case. Now, when the gravity is strong or extreme, we have to replace Newton's theory by Einstein's theory. But when the gravity is weak, Einstein's theory reduces to Newton's theory. So for most situations, it's perfectly good to use it. And so yes, Newton's theory, in terms of predicting your weight, if you like, on a planet or another body, is applicable anywhere. And so played out on Mars, it would predict that we would have 40% of the weight that we have on the Earth. If we went to the moon, we'd have about 15% of the weight we have on the Earth. And you can play this game with any object you like, a moon or a planet in our solar system or anywhere else around exoplanets, for example, around other stars. The principle applies there too.
Next question is from one of our live viewers. Dusk would like to know if a supernova was created, or I was going to say formed, near or in the Milky Way, how luminous would it be, and what would it look like from the Earth?
Well, we're sort of waiting, and we're long overdue. Based on the number of stars in our galaxy and our well-understood theory of star formation and evolution, we expect supernova somewhere in the Milky Way galaxy about every 100 years. That number used to be about every 50 years, but I think it's now about every 100 years. And if you look at the history, the last one we saw was in 1604. That's over 400 years ago. So we're way overdue. Now these occur by Poisson statistics. They're random. And so you can't say they happen every 100 years like a metronome with a periodicity. And so, for example, if a bus was due to come or a train every 10 minutes and you waited 40 minutes and you hadn't seen a train, you would not be entitled to assume that the trains stopped existing or the buses didn't operate at all. You just would figure you're bad luck. Traffic was bunched up and you just had to wait a long time. And that's the situation we're in. So basically we do expect a supernova to go off any year now, any time now. And as for what it would look like, it would be really impressive. The last two, which were the supernova of 1576 and the one of 1604, some astronomers like Tycho Brahe got to see two in their lifetimes, were visible to the naked eye briefly during a daytime sky. The Crab Nebula event, that was a supernova that went off in 1054, is represented in rock art and petroglyphs in the southwest where I live, and in Aborigine territory in Australia and all over the world actually. That was a visiting guest star, visible for several weeks actually in the daytime sky around the world. So these are pretty spectacular events. So in all probability, a supernova, if it goes off in our galaxy, in the region it's most likely to go off, which is towards the galactic center where there are more stars, will still be bright enough and close enough to the Earth to be visible in the daytime sky. So a truly spectacular event. Of course, be careful what you wish for. If that supernova goes off within close to the Earth, say 10, 15 light years, then it could be a catastrophic event for civilization and even for the biosphere of the Earth itself. So let's hope it's a safe distance where we get a really impressive light show in the sky, and that's all.
The next question is from one of our emails. The size of the central supermassive black hole is said to scale with the population of old stars in the galaxy. Can you talk a little bit about whether that's true and how that works?
Yes, this is a result from research over the last 20 years, actually. This result has been known for a while. As people started understanding that there are black holes in every galaxy, but that most of these black holes are not obvious because they're not bright, they're not fueling, then as the masses were measured, and when they're not bright and active, the way you measure the masses is by looking at the influence of the black hole on stellar orbits near the center of the galaxy or on gas motions. So using these motions as a proxy to measure mass, you can then compare the masses of all these black holes, with every galaxy having one, to the mass of the galaxy itself. If you compare it and do a correlation with the galaxy itself, the total galaxy mass, it's not actually a very tight correlation. But if instead you compare it to the mass of old stars in the galaxy, it's a very good correlation. It's accurate to about a factor of 2 or 2.5 over 3 decades, a factor of 1,000 or maybe even 10,000 in mass. In astronomy, that's a very good correlation over a large range. So what's special about the old star mass of a galaxy? First of all, what does that mean? That means that the biggest black holes you expect to be in elliptical galaxies, giant elliptical galaxies, because those are almost purely old stars and they're large and massive galaxies. So they indeed should and do have the biggest black holes. M87, good example, imaged by the Event Horizon Telescope last year. We expect, therefore, the smallest black holes to be in irregular galaxies like the Magellanic Clouds, or in late-type spiral galaxies where the bulge, that is the old stellar population, is quite modest. And the Milky Way is towards that end of the spectrum, and so we have a black hole that's only 4 million times the mass of the Sun. So the Milky Way sits on this correlation at the low end, and M87 sits on this correlation at the high end. And then the question becomes, why is there this correlation? It seems unusually good. And most astronomers think, without knowing for sure, that it's something to do with how the black holes form initially, early in the universe, seed black holes, much smaller than they are now, and how they grow. They grow in concert with the stars in the galaxy. And that makes sense at some point because galaxies also grow by mergers. And so as galaxies merge with each other, their black holes will merge and the masses will add. So it makes sense in an arithmetic sense that as galaxies merge and add together to get bigger, their black holes will merge and add. It tracks the old star population because that's the set of stars that are losing mass late in their lives, and that gas probably forms a large part of the fuel for the black hole, thereby helping the black holes get bigger. But I don't want to pretend this is a resolved question. There's active research to understand why these two quantities are so well correlated.
Kind of a related and follow-up question to that is, can telescopes now resolve stars in distant galaxies well enough to distinguish old stars from younger ones so that we could estimate the masses of black holes?
No, it's very hard to measure the mass of black holes in distant galaxies. The work that showed the correlation between black hole mass and old star mass in a galaxy was done on galaxies in the nearby universe, which is to say out to about 100 million light years. That's a really small fraction of the distance to the edge of the universe. Well, there are many black holes in the outer universe. They're in every galaxy, and there are active ones in quasars. And there we have a sort of different and more indirect method of measuring their mass. Basically, you take a spectrum of the quasar, that's the quasi-stellar radio source, the fueling phase of the black hole, and in the spectrum you see that the lines of hydrogen and other elements that comprise the chemistry of these objects are very broad, and these lines are indicative of the swirling gas near the center of the galaxy. And basically use Kepler's law, use a simple gravitational calculation to relate the speed of that gas moving near the center of that distant galaxy to the black hole that's driving those gas motions. So you don't ever see or have to see individual stars or even the gas cloud itself near the center of the galaxy. Use spectroscopy just as a single measurement, an unresolved measurement of the gas motions, and inferring that those gas motions or star motions from a dispersion are caused by the black hole, you can calculate the black hole mass. So with a single spectrum, you can get the mass of a distant galaxy that houses a quasar. And we've done this now for tens of thousands of quasars. So a lot of black hole masses have been published in the distant universe by this method.
The next question is from one of our live participants who would like to know, why doesn't the accretion disk's matter spill into the black hole? Why does it stay outside, and how does it do that?
Some of it does spill into the black hole, but the feeding of the black hole is actually a slow and methodical process. So remember, the black hole that forms at the center of a galaxy has a lot of angular momentum from all the material that went into it. And so by conserving angular momentum, the black holes are almost certainly spinning quite fast. And the material that swirls around them that forms the accretion disk also has a lot of angular momentum. And essentially, the accretion disk itself is supported or kept puffed up or kept at some size that just means it doesn't all fall straight into the black hole by this angular momentum. In other words, the mass cannot just fall radially into the black hole to make it grow bigger because it's maintained by a centrifugal force from this rotating disk. So the angular momentum of the disk plus the fact that it has a temperature, quite high temperature of hundreds of thousands of Kelvin, keeps that disk intact and means that mass only falls into the black hole from the innermost region, the inner edge, if you like, of the accretion disk. And models suggest that the inner region of the accretion disk is about 10 Schwarzschild radii away from the black hole. So the black hole's event horizon's distance is called the Schwarzschild radius in astronomy, and about 10 times that scale, or the size of the black hole, if you like, you have the inner edge of the accretion disk, and from that radius, from that orbit, mass can fall in on either a radial, a plunging orbit, or more likely spiraling in. But that's a very small fraction. That's a very slow feeding mechanism, sort of siphoning the inner part of the accretion disk onto the black hole, while most of the rest of the accretion disk is far from that radius and would have to lose angular momentum to fall into the black hole. So it's a very steady and slow process, in fact.
The next question is from Vikazoli, who's on with us live. Mars doesn't have a magnetic shield, so how much radiation would people get there compared to Earth? Is it safe to live on the surface of Mars, or would it be better to live under the surface?
That's right. Mars has no detectable or significant magnetic field. And that magnetic field is what shields a planet like the Earth, which has a magnetic field, from cosmic rays and high-energy radiation from the sun, essentially the solar wind, and also cosmic rays that are just traveling through the galaxy with very high energy. These are damaging particles and radiations that would cause mutations, cellular damage, and cancer, and so on. So we definitely need to be protected from those. It happens naturally on the Earth, and on Mars wouldn't. The estimate is that a round trip to Mars by astronauts taking the minimum time of about 8 months each way, plus a couple of months on the surface, would subject with moderate shielding in the spacecraft and as moderate shielding on the surface, would give the astronaut as much radiation, several times the radiation dose of their entire natural life on the Earth. In other words, in a little over a year, you're going to get more than a lifetime's worth of radiation. Increases cancer risk. The research on that says the increase in the cancer risk is not actually huge. It may be 30 or 50%, maybe a bit more. So it's not a devastating radiation exposure, but of course, if we want a Mars base, then we're going to have to deal with this. So I think for short visits, it's not a problem. People will accept the risk. For long visits or Moon or Mars base, we need a solution. And the solution is, as the questioner suggested, to use building material on Mars, since it's far more expensive to bring that material in, use the Martian soil or regolith and simple electrochemical processes to turn it essentially into slump block or bricks. And then you build a habitat, probably inflatable dome, and then over the top of that you shield it with probably close to a meter thick worth of rock or brick made from Martian soil. At that point you're very well protected, because the astronauts on the Mars base are rarely, if ever, going to go outside. And so at that point, they don't have any long-term risk at all.
We are getting to the end of our session. I think we will take this one last question. Zahra Al-Saif would like to know, how would you go about proving to others that the Earth is not flat?
Yeah, it's a good question, especially because reading the surveys, there's a vociferous flat Earth community out there. You can look at Google Trends data, which allows you to search the frequency of web searches for certain terms, and flat earth searches started growing in 2014, 2015. They went through a peak in the US in 2017 when a couple of famous basketball players sort of said maybe the earth's flat, but they haven't gone back down. So there's a number of people who believe in this for whatever reason, but people believe in a lot of weird stuff. How would I demonstrate to someone that the earth is not flat? I might use an argument such as the argument the Greeks used, which is that in the situation of a lunar eclipses are not that rare, the Earth's shadow is cast onto the moon. And you can see that the Earth's shadow is a curve. And so knowing how the sun, earth, moon illumination works, it's obvious that only a spherical object can cast a circular shadow. So that would be an astronomical way of proving it. Another way, of course, is just to show any number of pictures that are being taken every day from the International Space Station. So International Space Station is orbiting the Earth every 90 minutes or so, taking pictures all the time. So you could just have a live feed up to the International Space Station and someone could just see it in real time. Okay, well maybe that's fake too. If people are going to be super skeptical, then it gets a little harder. Then you might actually have to, take them on a voyage, show them ships, masts, tall ships, disappearing masts over the horizon on a smooth sea with no atmospheric effects coming into play, and use other indirect methods to show that the Earth is round. So there are definitely ways to do it, any number of them, and so I think any skeptic should be convinced by some or all of these methods. Good question to end with. We covered a lot of ground as usual. Excellent questions today, and we'll be back with you in the next week or so, and I guess we'll announce the next few sessions soon. Thank you. Thanks to Matthew for facilitating, and behind the scenes Alexander for technology support.
And then just quickly before we go, I just want to wish one of our mentors, Christy Reed, is apparently having surgery, and we just want to wish you good health and good luck with that.